In this example we will carry out dynamic simulations to examine the undervoltage ride-through behavior of a group of wind turbines. Activate the study case 6.1 UVRT simulation 0%. As you can see, the grid contains 6 wind turbine models. Each turbine model includes a model of its control system. Looking at an individual control system in detail, you can see that the control system contains measurement devices and a number of different controllers. For example, a real and reactive power controller is included as well as a current controller. Many of the controllers are constructed as a block diagram. Let's look at the current controller block diagram as an example. In the Data Manager, find the wind turbine model folder as shown. Right-click on the current controller block definition and select Show Graphic. Here you can see the current controller block diagram. There are a number of input signals including a real current reference and a reactive current reference. 2 PI controllers are included and you can see output signals leaving the controller. Return to the Grid tab. In this example, we will apply a fault very close to the point of common coupling. This will cause the voltage at the point of common coupling to fall to 0 volts. Typically under these circumstances, a wind turbine will need to inject additional reactive current into the network. We are going to carry out a dynamic simulation to demonstrate this behavior. Ensure that the RMS EMT simulation toolbox is selected. In this simulation, we will apply a 3-phase short circuit very near to the point of common coupling. This can be seen in the simulation events queue. It can be seen that this short circuit will be applied at 0 seconds and it will be cleared again after 100 milliseconds. The location of the 3-phase short circuit can be shown in the graphic by right-clicking the short circuit event and selecting Mark in Graphic. The short circuit is calculated at switch bay 3. Due to the fact that there is no fault impedance, the voltage at the bus bar will drop to 0 volts. After 100 milliseconds the switch highlighted will open, in order to clear the fault. Calculate the initial conditions. Notice that a balanced RMS simulation will be carried out. Change to the Plot PCC tab and run the simulation for 1 second. The 3 plots show the variation of various parameters with respect to the simulation time. The top plot shows the variation of the voltage at the busbar of the wind farm substation with respect to time. It can be seen that when the short circuit is applied at 0 seconds, the voltage at this busbar reduces to 0 volts. It stays at this value throughout the fault, until the fault is removed at 100 milliseconds. At this point, the voltage rises back to its pre-fault value. In the second plot, the positive sequence current contribution from the external grid and from the wind farm are shown. It can be seen that during the fault the contribution from the grid is very high. The bottom plot shows the real and the reactive power contribution from the wind farm at the point of common coupling. It can be seen that during the fault, since the voltage at the point of common coupling drops to 0, the real and the reactive power at the point of common coupling also drop to 0. Select the Plot Wind Turbine 2.4 tab. Here you can see results associated specifically with one of the turbines. The top plot in blue shows the positive sequence voltage at the wind turbine terminals. It can be seen that during the fault the voltage collapses. But the voltage is not collapsed to 0 volts as at the point of common coupling due to the impedance between the point of common coupling and the turbine. The bottom plot shows the active and reactive current supplied by the turbine. The reactive current is shown in red and the active current is shown in green. It can be seen that prior to the fault that the active and reactive current are constant. As soon as the fault is applied, There is an initial reaction from the wind turbine, and then the voltage support mode for the fault ride-through begins to exert its influence. The reactive current shown in red quickly rises until it reaches a limit. This limit is determined by the controller and depends on the converter rating. The active current reduces. The active current is reduced since priority is given to the reactive current injection. Post-fault, the values return to their pre-fault values. Returning to the grid, and looking at a wind turbine controller model again, it is possible to see the parameters which control the fault ride-through behavior of the turbine. For instance, the K factor, which is the gain for the additional reactive current required for voltage support, is shown to be equal to 2. This can be edited as required. We will now carry out a undervoltage-ride-through simulation where the fault is assumed to be further away from the point of common coupling. This will result in a voltage drop of 30% of nominal voltage at the point of common coupling. Activate the study case 6.2. In this study case, a fault is applied near to the point of common coupling again, but a fault impedance is included, which will result in a voltage drop at the point of common coupling equal to 30% of its nominal value. This can be seen in the events queue. Notice that this time, the fault is cleared after 500 milliseconds. Calculate the initial conditions and run the simulation again for 1 second. Notice that because the voltage has not dropped to 0 at the point of common coupling, there is this time some real and reactive power transfer at the point of common coupling. Notice that the reactive power transfer is higher than the real power transfer. Changing to the wind turbine plot, notice that in this case the reactive current supplied by the turbine is not limited. The reactive current delivered is determined according to the voltage dip and the K factor.